let's do one other example. This is problem 55 from chapter 6. And this problem reads, a machine at a post office sends a package out of a chute and down a ramp to be loaded into delivery vehicles. It calculates the acceleration of the box. It asks you to calculate the acceleration of the box heading down the 10-degree slope, assuming a specific coefficient of friction, and then find the angle of the slope down which the box could move at a constant velocity. And we are taking friction into account, but we're ignoring air resistance. Okay. So here we go. We're going to go ahead. This is an inclined plane with friction. So I'm going to go ahead and draw my inclined plane. So here's my inclined plane. I have my surface here. And we're going to put a truck down here. Whoop, there's a little truck. We have our angle. That's 10 degrees. We're going to have a package that's going to slide down this slope like that. Okay, before I draw my free body diagram, I'm just going to kind of sketch in the forces here on the actual diagram. We've got gravity pointing down. That's gravity. We have our normal force pushing up perpendicular to the slope, and then we have our frictional force pointing out in that direction. And then this is the resultant force, MA, of it sliding down the slope. And the question here again is, we're going to first calculate the acceleration, and then we're going to calculate an angle which the package would slide down with a constant velocity. So with all the inclined plane problems, I like to do this where I take my slope and I rotate it so that it's horizontal. So that way, both the acceleration and the friction are only going to have one component. I'm only going to have to break up the gravity into components. See, there's my truck there, so you can see that I've rotated this. So there's my angle like that. Here's my package and my free body diagram. We are going to, again, gravity is still pointing down at the ground, so it has to be off at an angle, which makes that also theta. We have our frictional force pointing that way. We have our normal force pushing up like that. And then we're calculating MA in that direction. So now let's go ahead and calculate this. Again, our strategy here is we're going to draw a free body diagram, and then we're going to use Newton's law to figure out what the acceleration is. Okay, so let's go ahead and draw a free body diagram independent of all this stuff. So we just have N pointing up like that. We have N, we have F, friction, we have our gravity pointing down like that. So those are the forces acting, and the resulting force is going to be the sum of those forces. So there's our forces. Now we're going to break these up into components. So let's start with the X component. The X component here, we've got two. We have the gravity that is operating in this direction, this projected gravity here, and we have the friction. The friction is opposing the motion. Gravity is creating the motion. So based on the way I have this drawn, my X components are going to be minus mg, and then we have to take into account the sine of that angle because of where it is in the triangle. And then we have the friction operating in the opposite direction, so it's going to be plus the friction. But as you remember from your reading, friction is equal to our coefficient of friction times the normal force. And this problem gave us the coefficient of friction as being mu point 0.1. So I'm just going to write down mu n here. That's my frictional component. And then this is equal to m times the acceleration in the x direction. And I should probably go ahead and the normal is only in the y direction, so we don't need a vector symbol there. Okay, like that. And now in the y direction, we're going to have two forces. We have the normal force that's pushing up, and we have the y component of gravity, mg cosine theta, which is going down, and that's equal to 0 because there is no y component of the acceleration. Okay, so I look at these equations, and what we're trying to do is find a sub x, and we don't know what n is, we don't know what a sub x is, but we do know all of these other parameters. So I have two equations and two unknowns. I'm going to start by solving for n, and I'm going to get mg cosine theta, and then I'm going to go ahead and plug that back in to this equation up here. So if I do that, I'm going to get minus mg sine theta plus mu mg cosine theta is equal to max. And you'll notice my masses cancel. How fascinating. So it doesn't depend on the mass. And that means my acceleration is just equal to mu cosine theta minus, mu g cosine theta minus g sine theta. And if I go ahead and put 10 degrees in for that, I could figure out what the acceleration is. Now, just looking at this again, if I make theta equals 90 degrees for the significance here, if I make theta equal to 90 degrees, cosine of theta goes to 0, sine of theta goes to 1, and I just get g, which is what I would expect for free fall. So this makes sense in the limit. And this problem asks you to put 10 in for here and 0.1 in for there, and I could go ahead and do that. I could say a sub x is equal to 0.1 times, let's just use 10 for the acceleration due to gravity. We have the cosine of 10 degrees minus 10 times the sine of 10 degrees. And you can go ahead and pop that in your calculator and see what that is. Now the second part of this question, though, it says, what angle would you need to get this moving at a constant velocity? Okay, so if you wanted this to move at a constant velocity, then you could set this up to where the acceleration was 0, right? So the acceleration would be 0 if the acceleration is 0, then the velocity is staying constant. So if we do that, we can go ahead and just take this same equation. We have ax is equal to mu g cosine theta minus g sine theta, and we set that equal to 0. And when we do that, we get that mu g cosine theta equals g sine theta, and that gives us a relationship that says that mu is equal to sine theta over tangent of theta, which is the same thing as, cosine of theta, which is the same thing as the tangent of theta. So there's a relationship there that's completely independent of gravity, mass, anything else, that if you are given a coefficient of friction, there's a specific angle where that object's velocity is not going to change. The flip side of this is you can use this relationship to measure the coefficient of friction, because you could set a package onto the box, or set a package onto the plane, and then slowly lift the plane up until it just starts to move. And that angle, the tangent of that, would be a measurement of your coefficient of static friction, which is pretty cool.